The cosmos stretches out in an unimaginable vastness of stars and galaxies. Where did all of this come from? This is the ultimate mystery, the one question that has captivated scientists and philosophers for centuries. The search for an answer has led to some truly mind-bending and controversial theories that challenge our most basic understanding of reality. In the next few minutes, you will discover 25 of the most debated ideas about our cosmic origin, from the widely accepted to the wildly speculative. We will explore theories suggesting our universe is a hologram, a computer simulation, or just one bubble in an infinite multiverse. So what does it really mean for something to come from nothing? Our story of cosmic origins begins with a thunderous flash, the Big Bang. This is the leading scientific narrative, the one you likely learned in school. It tells us that our entire universe was once compressed into an unimaginably hot, dense point, a singularity which then began expanding at a ferocious rate. All the matter and energy that would ever exist, all the galaxies, stars, and planets, were forged in that first fiery moment. But this elegant story is not without its profound mysteries. The theory describes what happened immediately after that initial burst, but it remains completely silent on the most fundamental questions. What or who lit the fuse? What could have possibly caused the Big Bang to occur in the first place? And what, if anything, existed before that one single point of everything? The concept of a singularity itself is a major point of controversy. This is a point of infinite density where the known laws of physics, the very rules of reality as we understand them, simply break down and cease to have any meaning. For many scientists, this is a major red flag. It suggests that the Big Bang theory is not the ultimate answer, but merely a description of the aftermath. It is like hearing the echo of a gunshot and trying to describe the bullet without ever knowing what pulled the trigger. Critics argue it is an incomplete explanation, a placeholder for a deeper truth we have yet to uncover. This profound silence about a beginning led some scientists to propose a radically different cosmic vision, one where the universe simply always was. The steady-state theory emerged as the Big Bang's most formidable rival, painting a picture of an eternal and unchanging cosmos. It rejected the idea of a single explosive origin, arguing instead that the universe has no beginning and no end. It is infinitely old and will exist forever. To reconcile this eternal nature with the observed expansion of the galaxies, the theory proposed a fantastical idea. New matter is continuously and spontaneously created in the empty space between stars. This creation happens at an almost imperceptible rate, just a few atoms per cubic mile every century, but it is enough to maintain a constant density as the universe stretches. In this model, the overall look of the cosmos never changes, a perfect, infinite equilibrium. For a time, this was a battle of titanic ideas, but then a ghostly signal from the depths of space delivered a decisive blow. In the 1960s, two astronomers accidentally discovered the cosmic microwave background radiation, a faint afterglow that permeates all of space. This sea of microwave radiation is the cooled remnant of the universe's hot, dense youth, the echo of the Big Bang's initial fireball. The steady-state theory had no convincing explanation for this all-pervasive background static. It was the evidence that firmly placed the Big Bang as the dominant model of cosmic history. Yet, even in defeat, the steady-state idea has not entirely vanished. A small number of cosmologists still find an elegant appeal in its simplicity. It completely sidesteps the philosophically troubling question of a beginning, the need for a first cause that the Big Bang theory inherently possesses. If the universe truly had no start, then we never have to ask what came before. This timeless cosmos remains, for some, a beautiful and less problematic alternative to the violent singularity from which our current understanding says everything was born. But what if the Big Bang was not a unique event, but merely one chapter in an endless cosmic story? This is the promise of the cyclic model, an idea that replaces the single explosive beginning with an infinite rhythm of death and rebirth. Imagine a universe that expands, reaches a limit, and then collapses back upon itself in a cataclysmic big crunch, only to rebound in a new Big Bang. Our entire cosmic history, from the first stars to the last black holes, would be just one cycle in an eternal series. This theory offers a beautifully simple answer to the troubling question of what came before. There was simply another universe and another before that, in an infinite chain with no beginning and no end. It is a cosmic heartbeat, a perpetual dance of creation and destruction. Yet this elegant vision faces a formidable scientific obstacle. Each cycle, according to the laws of thermodynamics, would generate an immense amount of disorder or entropy. This entropy should accumulate from one universe to the next. If that is true, then each new universe should start in a progressively more chaotic and disordered state. Our own universe, however, began in a state of remarkably low entropy, incredibly smooth and ordered, which allowed for the formation of galaxies and stars. Why would our cycle be so special if an infinite number of messy ones came before it? The theory must also explain the physics of the bounce itself. What force could possibly overcome the gravitational collapse of an entire universe and cause it to spring back into a new expansion? While some models suggest quantum gravity effects could provide this repulsive force, we currently have no direct evidence of a previous universe or the mechanism that would enable this cosmic rebound. The cyclic model resolves one profound mystery only to present us with new, equally challenging puzzles about the fundamental nature of reality. The elegant rhythm of a cyclic cosmos is not the only alternative to a single beginning. Another idea pushes the boundaries of reality even further, suggesting our entire universe is merely one isolated bubble in an infinite, frothing sea of other universes. This is the multiverse hypothesis. It proposes that our Big Bang was not a unique, singular event, but a local happening within a much grander, eternal meta-reality. In this view, the cosmos is constantly giving birth to new pocket universes through a process called eternal inflation. Think of a vast, bubbling pot of water that never stops boiling. Our universe is just one of countless bubbles that form, expand, and drift apart in this unimaginably vast cosmic foam. Each of these bubbles could be a completely separate reality, born with its own unique set of physical laws and fundamental constants. In one universe, gravity might be a repulsive force preventing planets from ever forming. In another, the nuclear forces that bind atoms together could be so weak that matter instantly flies apart. We just happen to live in the one bubble where the numbers are perfectly tuned for stars, planets, and life to exist. This is not the only version of a multiverse. Another emerges from the strange world of quantum mechanics, known as the many worlds interpretation. Here, every time a quantum particle faces a choice, the entire universe splits into multiple branches. In one branch, a radioactive atom decays, while in another, it does not. Every possible outcome of every single event actually occurs, spawning an endless tree of parallel realities where every decision you have ever made plays out in an infinite number of ways. The controversy surrounding the multiverse is not about its mathematical elegance, but its very nature as a scientific idea. The most powerful criticism is its fundamental untestability. By definition, these other universes are permanently beyond our observational horizon, causally disconnected from our own. We can never see them, measure them, or interact with them in any way. For many scientists, this makes the multiverse a metaphysical concept rather than a scientific one. A core principle of science is that a theory must be falsifiable, meaning there must be a conceivable way to prove it wrong. If no observation or experiment can ever contradict the multiverse idea, is it still science, or has it crossed into the realm of philosophy and speculation? Proponents counter that the multiverse is a natural prediction of our best theories of inflation and quantum mechanics, and that its indirect effects might one day be found etched into the fabric of our own cosmos. Yet the debate rages, forcing us to ask a profound question about the limits of knowledge itself. How far can scientific inquiry go when the evidence might be forever locked away in a reality we can never touch? Perhaps the most direct challenge to our experience of reality comes from the holographic principle. This radical idea, emerging from the depths of string theory and black hole physics, proposes a stunning possibility. Everything we perceive in our three-dimensional world, the depth of space, the solidity of matter, even our own conscious experience, might be an incredibly complex hologram. It suggests that all the information needed to describe our universe is actually encoded on a distant, two-dimensional surface that surrounds us, like the information on a DVD, creating the illusion of a three-dimensional movie. Think of the shimmering, three-dimensional image on your credit card. It appears to have volume and depth, yet it is all contained on a flat, two-dimensional plastic sheet. The holographic principle argues our universe operates on a similar, though infinitely more sophisticated, cosmic scale. We are, in essence, living inside a projection. The controversy this theory ignites is immediate and profound. It strikes at the very core of what we consider to be real. How can the rich, three-dimensional reality we move through every day, the feeling of wind on your skin or the vast distance to a star, be nothing more than a shadow play? The implications are dizzying. If true, it would mean that the fundamental building blocks of reality are not particles or strings in three dimensions, but bits of information like the ones and zeros in a computer, stored on a flat surface at the edge of the cosmos. This is not merely a philosophical curiosity. The holographic principle found its first serious application in solving one of the most stubborn puzzles in physics, the black hole information paradox. A black hole, according to classical physics, should permanently destroy any information about the matter that falls into it. This violates a fundamental tenet of quantum mechanics, which states that information can never be truly lost. The holographic principle offers an elegant solution. It suggests that all the information about the object swallowed by a black hole is not destroyed, but is instead perfectly preserved, encoded on the black hole's two-dimensional event horizon, the point of no return. The information is scrambled, but it is not gone. This resolution, while mathematically beautiful, highlights the theory's greatest weakness. It remains one of the most speculative ideas in modern physics. The mathematics involved is formidably complex, and as of now, there is no direct experimental evidence to confirm that we are indeed living in a cosmic hologram. We are left with a theory that brilliantly solves deep theoretical problems while fundamentally undermining our perception of the universe, leaving us to wonder if the very space we inhabit is the ultimate illusion. The idea that reality itself might be an elaborate fabrication finds its ultimate expression in the simulation hypothesis. This theory pushes beyond the holographic principle to suggest that our entire universe, from the smallest atom to the largest galaxy, is not the foundational layer of existence. Instead, it proposes we are living inside a sophisticated computer simulation, much like a video game, built by a civilization with technology so far beyond our own that their digital creation is indistinguishable from reality. The argument was famously formalized by the philosopher Nick Bostrom, who laid out a compelling trilemma. He suggests that at least one of three propositions must be true. Either nearly all civilizations like ours go extinct before reaching a post-human stage, or any such advanced civilization has absolutely no interest in running simulations of its own history, or we are almost certainly living in a simulation. If a civilization does survive its technological adolescence and does choose to run such simulations, it could create astronomical numbers of them. The simulated minds would vastly outnumber the original biological ones, making it statistically more likely that we are among the simulated. This line of thinking has found surprising support from some tech leaders who point to the rapid advancement of our own computing power and virtual reality as a glimpse of a future where creating such a universe might be possible. Yet this idea is met with fierce resistance from much of the scientific community. Many physicists dismiss it not as science, but as a modern form of creationism, simply replacing God with a programmer. Their core criticism is brutal in its simplicity. The simulation hypothesis, they argue, offers no testable predictions. It does not explain why the speed of light is what it is, or why gravity follows an inverse square law. A programmer could have set these constants to any value, so the theory provides no explanatory power for the actual laws of physics we observe. It is a philosophical speculation, they say, one that is ultimately untestable and therefore lies outside the realm of science. Is our reality a cosmic calculation running on some alien supercomputer? Or is this hypothesis merely a captivating story that tells us more about our own technological anxieties than about the true nature of the cosmos? While some theories question the very fabric of reality, another challenges the fundamental forces that govern it. The plasma universe, also known as the electric universe, proposes a cosmos not ruled by gravity, but by the immense power of electromagnetism. In this alternative vision, the primary state of matter is not neutral gas, but plasma, a searingly hot, electrically charged soup of particles that makes up most of the visible universe. Proponents argue that vast, flowing electric currents course through the emptiness of space, shaping galaxies, powering stars, and sculpting planetary landscapes on a scale that gravity alone cannot explain. This is a universe in a state of perpetual electrical dynamism, often without a beginning or an end, fundamentally opposing the Big Bang narrative. It suggests that stars are not powered solely by internal nuclear fusion, but by immense electrical currents flowing in from galactic circuits, and that the familiar scars on planets like Mars were carved not by water, but by planetary-scale electric arcs. This radical reinterpretation of cosmic history is, however, the source of its intense controversy. Mainstream astrophysics has largely rejected the electric universe model. The criticism is twofold. First, its core predictions consistently clash with a mountain of established observational evidence. The theory struggles to account for the precise characteristics of the cosmic microwave background, that faint afterglow of the Big Bang, and it cannot explain the observed cosmic abundances of light elements like hydrogen and helium, which are perfectly explained by Big Bang nucleosynthesis. Second, and perhaps more damning in the eyes of physicists, the theory lacks the rigorous mathematical framework that underpins general relativity and the standard model of particle physics. It often relies on qualitative descriptions and visual similarities, such as comparing galactic structures to laboratory plasma discharges, without providing the quantitative, predictive power that defines a robust scientific theory. Is the cosmos a grand electrical phenomenon that we have simply failed to properly measure? Or is this a compelling but ultimately flawed narrative that overlooks the dominant role of gravity in shaping our universe? There is another perspective that stands in stark contrast to all these scientific models, one that finds its answers not in equations but in divinity. Creationism and the related concept of intelligent design propose that the universe and all life within it are the deliberate work of a supreme, intelligent being. This view holds that the cosmos shows evidence of purposeful design, far too complex to have arisen from random, unguided processes. Proponents often point to the precise fine-tuning of the universe's physical constants, arguing that if gravity or the nuclear forces were even slightly different, life could never have formed. For them, this perfection is not a fortunate accident, but the signature of a creator. This perspective is frequently supported by specific interpretations of religious texts, which are presented as historical accounts of creation that directly challenge the timelines and mechanisms of both the Big Bang and biological evolution. The resulting controversy is not merely a scientific debate, but a profound cultural and philosophical clash over the very sources of knowledge. From a scientific standpoint, however, creationism and intelligent design are not classified as scientific theories. The core issue lies in the nature of their proposed explanation. Science, by its definition, seeks natural causes for natural phenomena through hypotheses that can be tested, verified, and potentially proven false through observation and experiment. Intelligent design, by invoking an untestable supernatural designer, does not offer a natural mechanism that can be examined or falsified. It does not make specific, predictive claims about what we should find in the fossil record or the cosmic background radiation that could then be checked against the evidence. Instead, it often functions as an argument against the current scientific explanations, pointing out perceived gaps or complexities as proof of divine intervention. This fundamental difference in methodology places the idea in a separate category of inquiry, one of theology and philosophy. The conflict arises when these two different ways of understanding the world are presented as being in direct competition for the same explanatory territory. Science asks how the heavens go, while this particular philosophical view asks how to go to heaven. They are framed as answering fundamentally different kinds of questions, which is why the debate over teaching intelligent design in science classrooms remains one of the most heated and enduring controversies about our origins. But from the elegant chaos of plasma and the silent arguments of design, we move to a theory that finds the origin of our universe in a single, violent, and spectacular accident. The ekpyrotic universe envisions our cosmic beginning not with a bang from a single point, but with a shattering collision between entire worlds. This idea emerges from the depths of string theory, which suggests that the fundamental constituents of reality are not particles, but tiny, vibrating strings. To make the mathematics work, string theory requires more than the three spatial dimensions we experience. It proposes the existence of extra, hidden dimensions, curled up so small that we can never perceive them. The ekpyrotic model takes this a dramatic step further. It posits that our entire universe is a three-dimensional membrane, or brane for short, existing within this higher dimensional space. And we are not alone. Other three-dimensional branes could be floating in this bulk, like immense, invisible sheets separated by a tiny gap. The theory suggests that our Big Bang was the moment our brain collided with another parallel brain. This cosmic collision did not create matter and energy from nothing. Instead, it took the pre-existing energy of the two colliding worlds and funneled it into an explosive expansion, creating the hot, dense universe we recognize from the Standard Model. It replaces the mystery of the singularity with the physics of a high-energy impact. This idea elegantly solves some of the puzzles that plague standard cosmic inflation, such as why our universe appears so remarkably flat and uniform on large scales. A slow, gentle collision between branes would naturally smooth everything out before the big rebound. Yet the controversy surrounding the ekpyrotic universe is as profound as its premise. The entire framework rests upon the unproven foundation of string theory and the existence of extra dimensions, neither of which have any direct experimental confirmation. We are asked to accept the reality of realms we can never see or touch. Furthermore, the theory introduces its own immense complexities. What set the branes in motion toward each other? What are they made of, and most critically, where is the evidence? If another brane exists parallel to our own, its gravitational influence might one day be detected, but so far, no such signal has been found. We are left with a compelling story of a cosmic car crash that explains our birth, but one that remains, for now, a beautiful and untested piece of theoretical physics. From a cosmic collision, we now journey to a vision of time itself as a perfect, repeating circle. Roger Penrose, a Nobel laureate in physics, presents a theory so elegant it feels almost poetic, the conformal cyclic cosmology. It proposes that our universe is not the first and only one, but merely one eon in an endless, infinite series. In this model, the universe does not end in a cold, dark fade or a violent crunch. Instead, as it expands forever and all matter eventually decays into radiation, something profound happens. The universe becomes so vast, smooth, and featureless that it loses any sense of scale. At this distant, faded end of time, the geometry of spacetime undergoes a conformal rescaling, a mathematical transformation that effectively resets the clock. The infinite future of our old, dead universe seamlessly becomes the hot, dense, low-entropy singularity of the next Big Bang. The end is literally the beginning in an endless, timeless loop. To support this breathtaking claim, Penrose points to what he calls Hawking points, mysterious concentric circles of slightly warmer temperature within the cosmic microwave background radiation. He believes these are the final, fading imprints of supermassive black holes from the previous eon, their Hawking radiation emissions stretched across the sky by the conformal rescaling process. It is as if we are seeing the ghostly fingerprints of a dead cosmos imprinted on our own. Yet this evidence is the very heart of the controversy. The vast majority of cosmologists remain deeply skeptical. They argue that the statistical analysis used to identify these Hawking points is fundamentally flawed. The patterns Penrose sees, they contend, are exactly what you would expect to find by random chance in the incredibly complex map of the CMB. When other teams reanalyzed the same data with different methods, the alleged signal disappeared. There is also a deep theoretical challenge. The theory requires that each new eon begins in a state of incredibly low entropy, perfectly smooth and ordered to allow for the formation of galaxies. But if the previous universe ended in a state of maximum disorder, a featureless sea of radiation, how does the next one reset to such a pristine, low-entropy state? This seems to violate the second law of thermodynamics, which states that the total disorder of a closed system can only increase. Penrose suggests that the conformal rescaling itself resets the entropy clock, but this remains a deeply puzzling and unproven aspect of the model. So we are left with a choice between a beautiful, cyclic symmetry and the cold, hard statistics of data. Is the cosmos whispering to us of its past lives through these faint rings in the sky? Or are we simply seeing patterns in the cosmic static, a story we desperately want to be true? The elegant cycles of eons give way to an even more startling possibility, that we are not living in a universe at all, but are instead inhabitants of a cosmic tomb. Black hole cosmology proposes that our entire expanding cosmos exists within the interior of a black hole, and that every black hole we observe is itself the seed of a brand new universe. This is the fecund universe, a self-replicating multiverse where reality breeds more reality through gravitational collapse. In this model, the Big Bang singularity was not a true singularity in the classical sense, but rather the dense, energetic interior of a black hole's core as perceived from within. When a massive star collapses in its parent universe, it forms a black hole, but from our perspective, that collapse is our own explosive beginning. The event horizon of that parent black hole becomes the cosmological horizon of our new universe, the ultimate boundary beyond which we can never see. This idea offers a potential solution to the vexing singularity problem of the Big Bang. General relativity predicts a point of infinite density where its laws fail. But if our universe was born from a black hole, the physics of that parent universe would apply at the moment of our birth, preventing a true physical infinity. Our universe's origin would be a tremendously dense but finite transition. The controversy here is as immense as the idea itself. Critics point to formidable mathematical and conceptual hurdles. The theory struggles to explain the specific, observed properties of our cosmos. A generic black hole formed from a collapsing star would not necessarily produce a universe that is so remarkably flat, uniform, and endowed with the precise initial conditions that allowed for galaxies to form. Why is our universe so perfectly tuned if it was born from what should be a chaotic gravitational catastrophe? Furthermore, the mechanism for how the interior of a black hole transitions into an expanding universe like our own is not well understood and requires speculative physics that goes far beyond current confirmation. We are left with a hauntingly beautiful vision of cosmic ancestry, where every pinprick of darkness in our night sky is an entire reality, a universe within a universe. But is this a profound insight into the layered nature of existence, or a mathematical mirage that creates more problems than it solves? The haunting idea of universes nesting within black holes confronts a profound and unsettling observation about our own reality. Our universe is not just habitable, it appears to be suspiciously fine-tuned for life. The fundamental constants of nature, the numerical values that govern the strength of gravity, the nuclear forces, and the speed of light, seem to be set with impossible precision. If the force that binds atomic nuclei were just a few % weaker, only hydrogen would exist and no complex atoms could form. If it were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no water or the chemistry of life. If the force of gravity were a tiny bit stronger, the universe would have collapsed back on itself long before stars ever formed. This apparent perfection is the domain of the anthropic principle, a philosophical argument that attempts to make sense of our privileged position in the cosmos. The weak anthropic principle offers a simple, almost self-evident explanation. It states that we can only observe a universe that has the properties necessary for our existence as observers. In other words, we are here to see these constants because if they were any different, we would not be here to see anything at all. It is a selection effect, like a lottery winner marveling at their incredible luck without considering the millions who lost. The universe does not seem fine-tuned for life in general, but specifically for the kind of life that can arise and ask these very questions. The strong anthropic principle takes a much bolder and more controversial step. It argues that the universe must have properties that allow life to develop at some stage in its history. This version suggests there is some underlying law or necessity that compels the cosmos to be bio-friendly. It hints at a deeper design or a fundamental principle of physics that mandates the emergence of conscious observers. The controversy here is fierce and fundamental. Many scientists dismiss the anthropic principle, especially its strong version, as a tautology, a circular argument that explains nothing. It simply states the conditions of our observation without providing any physical mechanism for why those conditions came to be. It is not a scientific theory that can be tested, but a philosophical statement about our place in the universe. Yet for others, the fine-tuning is too glaring to ignore, and the anthropic logic becomes a crucial clue. If our universe is just one of a vast multiverse, each with randomly different physical constants, then it is no surprise we find ourselves in the one rare bubble where the numbers are just right. In this view, the anthropic principle is not an explanation in itself, but a guiding tool for navigating a much larger, more random cosmic landscape. The debate forces us to confront a difficult question. Are we the beneficiaries of a staggering cosmic coincidence, or does our very presence as observers tell us something fundamental and necessary about the structure of reality itself? This elegant symmetry of time confronts the most stubbornly one-way street in all of physics. We experience time as a relentless flow from past to future, an arrow that never reverses. This directionality is enshrined in the second law of thermodynamics, which states that the total disorder or entropy of a closed system must always increase. An ice cube melts in a warm drink, a shattered glass never reassembles itself, and memories are only of the past. The universe, from our perspective, is running down. The time-symmetric universe theory makes the radical proposal that this is an illusion, a local perspective within a much grander, perfectly symmetrical reality. It suggests that the Big Bang and a potential future Big Crunch are not two separate events, but are in fact one and the same moment in time. Imagine time not as a straight line, but as a perfect circle. From our point on the circle, we perceive a past leading to the Big Bang and a future leading to a Big Crunch. But if you could step outside of time, you would see that the bang and the crunch are identical, a single point of maximum connection. In this view, the universe expands from that point, reaches a maximum size, and then contracts back to it. The catch is that during the contraction phase, the arrow of time would theoretically reverse. From the perspective of beings in that contracting phase, their past would be our future, and their future would be our past. They would see broken glasses reassembling and heat flowing from cold objects to hot ones, all while believing they are moving forward in time just as we do. The controversy this ignites is immediate and profound. It directly assaults our most fundamental understanding of cause and effect. If the future can influence the past just as the past influences the future, then what does causality even mean? The theory struggles mightily to explain why we only remember the past if the future is just as real and connected. Why does our entire conscious experience and every physical process we have ever observed so stubbornly obey the second law of thermodynamics if the underlying laws of physics are truly time-symmetric? Proponents argue that the low entropy state of the Big Bang is not a special starting condition, but a boundary condition that applies to both ends of time. The universe must have low entropy at the Big Bang and also at the Big Crunch, forcing a symmetrical evolution. Critics, however, point out that we see no evidence of this. Our universe shows no signs of being prepared for a graceful, low-entropy collapse. All the evidence suggests it is headed for a cold, dark, and maximally disordered end, not a symmetrical reversal. Reconciling this beautiful, symmetric theory with the messy, one-way reality we actually inhabit remains one of the most difficult challenges in theoretical physics. This fine-tuning leads to one of the most radical reinterpretations of our cosmic role. John Wheeler's participatory anthropic principle pushes the idea of a bio-friendly universe to its logical and startling extreme. It suggests that observers are not just accidental beneficiaries of the cosmos, but necessary participants in its very existence. In this view, the universe only becomes real, only solidifies into a definite state through the act of observation by a conscious mind. We are not just living in the universe, we are bringing it into being. Wheeler found the inspiration for this mind-bending idea in the heart of quantum mechanics, where the act of measurement famously changes the system being measured. In the classic double-slit experiment, a single particle like an electron behaves as a wave, passing through both slits simultaneously and creating an interference pattern. But the moment a scientist places a detector to see which slit the electron goes through, the wave-like behavior vanishes. The particle chooses a single path as if it knew it was being watched. Wheeler proposed a cosmic-scale version of this experiment, using the light from distant quasars bent by intervening galaxies. He argued that the decision to measure the path of a photon today could, in principle, influence the state that photon was in billions of years ago. It is as if the universe remains a blurry cloud of possibilities, a set of potential histories, until a conscious observer looks back and forces it to choose a specific path. The controversy here is immense and immediate. Critics argue this idea ventures far beyond science into the realm of pure philosophy. How could you possibly test such a claim? If the universe requires a conscious observer to exist, then who was observing the universe during its first billion years before any life evolved? Was it in a ghostly, unrealized state? Proponents might counter that the universe is a self-exciting system, where later observers retroactively crystallize the early cosmos, but this sounds suspiciously like magic to many physicists. The principle is also accused of bordering on solipsism, the philosophical idea that only one's own mind is sure to exist. More fundamentally, it turns the standard scientific story on its head. Mainstream science views consciousness as an emergent property, a complex phenomenon that arises from the intricate wiring of billions of neurons in a brain. The participatory anthropic principle suggests the opposite, that consciousness is a primary, fundamental force of nature, as basic as space and time. This places the human mind, or any conscious mind, back at the center of the cosmos in a way not seen since before the scientific revolution. Are we the universe's way of knowing itself, or is this a beautiful, untestable story we tell ourselves to feel significant in a vast and indifferent cosmos? Before our modern telescopes pierced the depths of space, the cosmos was seen as a perfect, unchanging vault. This idea of a static universe, eternal and fixed in size, was the default assumption for millennia, a comforting constant in the human understanding of the heavens. It was a universe without a story, without a beginning or an end, where the galaxies were thought to be permanent fixtures in a celestial tapestry. This ancient belief was shattered in the 1920s by the work of Edwin Hubble. By meticulously observing distant galaxies, he made a staggering discovery. The light from these galaxies was systematically shifted toward the red end of the spectrum, a phenomenon known as redshift. This was not just a curious color change, it was a cosmic speedometer. Hubble interpreted this redshift as a Doppler effect, the same phenomenon that makes a siren's pitch drop as it races away from you. The inescapable conclusion was that nearly all galaxies are flying away from us, and from each other, meaning the very fabric of space itself is stretching. The universe was not static at all, it was dynamically expanding, blowing the timeless cosmos of old to pieces. This discovery was the final, definitive evidence that banished the static universe from mainstream science and cemented the reality of the Big Bang. Yet, a stubborn controversy persists in the form of the tired light hypothesis. This alternative explanation attempts to rescue a form of the static universe by proposing that light simply loses energy and therefore becomes redder as it travels across the vast cosmic distances to reach us. Perhaps the idea goes, light interacts with interstellar dust or some unknown field, gradually getting tired on its long journey, which creates the illusion of recession without any real expansion. The problem is that tired light cannot explain the full suite of evidence. If redshift were only due to light getting tired, then the light from distant supernova explosions would not show the clear signs of time dilation that we observe. Astronomers see that the light curves of these immense stellar explosions are stretched out, their brightening and fading happening in slow motion. This is exactly what you would expect in an expanding universe where the stretching of space itself stretches the duration of the light's journey. A static, tired light universe has no such mechanism. It predicts we would see these cataclysmic events unfold at the same rate, regardless of distance, which is definitively not what our telescopes reveal. The static universe offers a simpler, more intuitive picture, but it is a picture that fails to match the moving, evolving, and deeply dynamic reality we actually see. At the heart of the Big Bang lies a violent paradox, a place where gravity becomes so strong that quantum mechanics must take over. This is the domain of quantum gravity, a theoretical frontier where physicists attempt to rewrite the story of our cosmic origin by unifying Einstein's theory of gravity with the bizarre rules of the quantum world. One of the most compelling visions to emerge is loop quantum cosmology. It paints a picture where the universe does not emerge from a true singularity of infinite density. Instead, think of space itself as woven from a fabric of tiny, finite loops, a billion times smaller than an atom. As we rewind time, the universe gets denser and hotter, but these loops of space resist complete collapse. They reach a point of maximum compression, and then a cosmic repulsion takes over, causing a great bounce. Our Big Bang was not a beginning from nothing, but a rebound from the death of a previous cosmic cycle. This big bounce elegantly avoids the mathematical nightmare of a true singularity, replacing a definitive start with an eternal, cyclical rhythm. Yet another profound idea seeks to erase the beginning of time entirely. The no-boundary proposal, developed by James Hartle and Stephen Hawking, uses the strange tools of quantum mechanics to describe the universe as entirely self-contained. It has no boundary, no edge, and no beginning, in much the same way that the surface of the Earth has a finite area but no starting point. If you travel back in time, the character of time itself smoothly changes, becoming more like a direction in space. The universe would simply be, without a moment of creation, much like the North Pole is a location on our planet, but not an edge from which the Earth emerges. The controversy surrounding these theories is as deep as their implications. They are built on some of the most complex mathematics known to physics, a language so abstract that it can be nearly impossible to translate into the intuitive concepts of cause and effect we rely on. How can we truly grasp a reality where time, the very framework of our existence, loses its fundamental meaning? The most significant challenge, however, is the complete lack of experimental proof. These are beautiful, self-consistent stories written in the language of mathematics, but we have no telescope or particle accelerator that can peer into that first moment to confirm if the bounce occurred or if time truly has no boundary. They stand as magnificent possibilities, reminding us that our search for ultimate origins may forever push against the very limits of human comprehension. Perhaps the greatest illusion is the idea of a beginning itself. For all its power, the Big Bang theory may have led us to a mirage, a point in our equations that signals not the start of time, but the limit of our understanding. Some physicists argue that the initial singularity is not a real physical event. It is a mathematical warning sign, a place where Einstein's theory of general relativity, our best description of gravity, simply stops working. The equations spit out infinities for density and temperature, which in physics is a clear indicator that you have pushed a good theory far beyond its breaking point. It is like using a road map to navigate the open ocean. The map is useful until you leave the shore, and then it becomes meaningless. The singularity, in this view, is not a place where the universe began, but a place where our current knowledge ends. The true nature of our cosmic origin, they insist, is waiting to be discovered in a unified theory of quantum gravity, a framework that can describe the intense, microscopic conditions where gravity and the quantum world collide. This is where the controversy cuts to the very heart of our inquiry. Are we even asking the right question when we search for a beginning? Our entire concept of time is built from our experience in a calm, classical universe. We perceive it as a smooth, flowing river moving from past to future. But at the extreme energies of the cosmos's first moment, this river might have been a chaotic waterfall, or it might not have existed as a dimension at all. In the quantum realm, time can become fuzzy and ill-defined. What if the question of what came before the Big Bang is as meaningless as asking what is north of the North Pole? The point is not a location in time, but a boundary where time, as we know it, ceases to have any coherent meaning. This perspective forces a profound shift. We are not detectives looking for a cosmic criminal who lit the fuse. We are explorers trying to understand a landscape where the very concepts of before and after may dissolve into a more fundamental, timeless reality. The search for a beginning might be the very thing preventing us from seeing the true, and perhaps beginningless, nature of the cosmos. This radical perspective dissolves the boundary between the physical world and the abstract realm of numbers. The mathematical universe hypothesis, championed by physicist Max Tegmark, proposes a staggering idea. Our cosmos is not merely described by the language of mathematics, which is powerful enough on its own. Instead, the universe is mathematics. Every star, every atom, and every conscious thought is part of a vast, formal mathematical structure, and we are self-aware patterns, complex computations running within that structure. In this view, the universe does not obey mathematical laws, it is those laws. The equations are not a map of the territory, they are the territory itself. This is a modern form of Pythagoreanism, an ancient belief that numbers are the ultimate substance of reality, taken to its absolute extreme. The hypothesis suggests that all structures that exist mathematically also exist physically. This leads to a breathtaking and, for some, terrifying implication. Every possible universe that can be described by a consistent set of mathematical equations must, by definition, be just as real as our own. There is a mathematical structure describing a cosmos with 7 spatial dimensions and purple stars, and that cosmos exists. There is a structure defining a universe where gravity is 1,000 times stronger, and it too is real. Our particular reality is simply the one mathematical structure that we, as a substructure within it, happen to perceive. The controversy this ignites is as fundamental as it gets. For proponents, this is the ultimate form of Occam's razor, a way to strip away unnecessary metaphysical baggage. It eliminates the need for a mysterious, nebulous substance called physical reality that exists independently of the math. There is no mysterious stuff, only mathematical patterns and relations. The laws of physics are not programmed into the cosmos, they are the intrinsic properties of the structure we inhabit. Yet critics launch a powerful two-pronged attack. First, they argue the hypothesis is fundamentally untestable and therefore not science. How could you possibly design an experiment to prove that a triangle in geometry class is just as physically real as the mountain you're climbing? If every mathematical structure is real, then the theory can never be falsified because any observation we make is simply a feature of our particular structure. The second major criticism cuts even deeper. If all mathematical structures are equally real, then why does this one feel so concrete to us? What is the process that breathes fire into the equations, that instantiates this particular set of mathematical relations as the vivid, tangible world we experience? The hypothesis seems to describe a vast library of all possible books, but it does not explain why we are characters living inside one specific volume, feeling the weight of its pages and the heat of its sun. Are we truly just self-aware knots in the fabric of a cosmic equation? Or is this the final, desperate attempt to reduce the rich mystery of existence to a cold and silent set of symbols? But what if the ultimate cosmic free lunch is not a matter of divine will or mathematical necessity, but a simple, spontaneous event? Physicist Lawrence Krauss presents a provocative argument that our universe could have indeed emerged from absolutely nothing. This is not the poetic nothing of empty space, but a rigorous physical definition. Krauss defines nothing as the complete absence of space, time, and matter, a state of non-being that is inherently unstable. His theory points to the bizarre behavior of the quantum vacuum. Even in what we call empty space, the quantum world is never truly still. Virtual particles spontaneously pop into and out of existence, borrowing energy from the void for fleeting moments before annihilating each other. Krauss proposes that our entire cosmos could be the ultimate quantum fluctuation, a bubble of space-time that tunneled from this state of true nothingness into the expanding universe we see today. In this view, the Big Bang is not a singular event requiring a cause, but a statistical inevitability, a fluctuation on the grandest possible scale. The fiery controversy this idea ignites is not about the quantum mechanics, but about the very definition of nothing. Philosophers and some scientists launch a powerful counter-argument. They claim that the quantum vacuum Krauss describes is not truly nothing. It is a something, a physical system governed by the specific laws of quantum field theory and general relativity. These laws have specific properties and allow for specific behaviors like fluctuations. The question then simply shifts. Why is there a quantum vacuum with these particular laws that permit universes to spring into being? The theory, critics argue, brilliantly explains how something could come from a very peculiar kind of something, but it completely sidesteps the deeper, metaphysical question that has haunted humanity for millennia. Why is there a reality governed by any laws at all? Why is there something with its potential for quantum bubbles and cosmic histories rather than absolute, utter, and unconditional nothing? Krauss's argument provides a powerful mechanism for our universe's origin, but it leaves us standing at the edge of a much deeper mystery, staring into an abyss where even the laws of physics themselves demand an explanation. The smooth, timeless equations of Einstein hold a secret twin, a cosmic opposite to the all-consuming black hole. If a black hole is a one-way street where matter and energy vanish forever, then a white hole would be its explosive exit ramp, a region of space-time from which matter and energy can only pour outward but nothing can ever enter. This leads to a radical theory of our own origin, that the Big Bang was not a beginning at all, but the spectacular eruption of a white hole, a cosmic geyser spewing the material for our entire universe from a hidden source. In this vision, our universe was not born from nothing, but was violently ejected from another pre-existing reality, a parent universe where a black hole's collapse in one realm became a white hole's genesis in another. The controversy here is as stark as the black and white imagery. While the mathematics of general relativity does permit such a solution, it is a solution in a perfect, sterile vacuum. In the messy, dynamic reality we inhabit, white holes are considered physically implausible. Most physicists argue they are profoundly unstable, that any single particle of matter attempting to fall in would instantly collapse the entire structure back into a black hole. They are cosmic mirages, beautiful mathematical phantoms that could not persist for more than a fleeting instant, let alone long enough to birth an entire cosmos. Furthermore, we have absolutely zero observational evidence for their existence. Our telescopes have never detected a persistent, unexplained fountain of energy and matter in the void that fits this description. So we are left with a haunting possibility that our entire reality is the exhaust from another universe's cosmic engine. But without a single shred of evidence to confirm it, this idea remains a captivating ghost in the machine of theoretical physics, a shadow of a beginning that our universe may have left forever behind. This idea that information is the true fabric of existence pushes the holographic principle to its logical extreme. If our three-dimensional reality is a projection, then the solid objects we touch and the vast spaces we see are not the foundation of the cosmos. They are a translation, a complex output generated from a deeper layer of reality. At this fundamental level, the universe operates like a vast cosmic computer, and the bits of information stored on a distant two-dimensional boundary are the ultimate code. The particles that make up your body, the forces that hold atoms together, and the light from distant stars are all emergent properties, manifestations of this underlying information processing. Think of a modern video game. The immersive world you explore with its forests, cities, and characters feels tangibly real on your screen. Yet every tree, every shadow is generated in real time from a set of instructions encoded on the device's memory. The holographic universe suggests our reality works in a similar way, but on a cosmic scale. The screen is the two-dimensional boundary of our observable universe, and the processing power is the fundamental laws of physics themselves. This leads to a controversy that strikes at the very heart of materialism. What does it mean for something to be physical? We are accustomed to thinking of the world as made of stuff, of solid matter. But if that matter is just a holographic expression of information, then the physical world is a kind of illusion, a secondary effect. The true substance of reality is not tiny, vibrating strings or point-like particles, but abstract bits, the ones and zeros of existence. This forces us to reconsider everything from the nature of mass to the flow of time. Are they fundamental properties, or are they simply computed outputs? The boundary between physics and information science begins to blur, and we are left wondering if the universe is not a great mechanism but a great calculation. The question is no longer what the universe is made of, but what it is computing. The vast cosmic landscape of the multiverse is not a single, monolithic idea, but a concept that unfolds in distinct and progressively stranger layers. The simplest version is known as a Level 1 multiverse. This suggests that our observable universe, with its 100 billion galaxies, is merely a tiny, visible patch within an infinite, perhaps eternal, greater cosmos. Beyond the distance light has been able to travel since the Big Bang, space simply continues, dotted with more galaxies, more stars, and even more planets. Somewhere out there, far beyond our cosmic horizon, there could be an identical copy of you reading an identical copy of this script, simply because in an infinite expanse, every possible configuration of matter must eventually repeat. This idea is almost a direct consequence of an infinite, expanding universe, and while we can never see these distant twins, it doesn't require any new or exotic physics, making it the most palatable level for many scientists. But the real controversy ignites with the Level 2 multiverse. Here, we venture into the realm of eternal inflation, where our entire universe is just one isolated bubble in a frothing, chaotic sea of newborn realities. Each of these bubbles forms with its own unique, random set of physical constants. In one bubble universe, gravity might be so strong that stars burn out in 1,000,000 years, while in another, the nuclear forces are too weak to form atoms at all. We simply exist in the one rare bubble where the numbers are, by pure chance, perfect for our existence. This directly addresses the profound mystery of our universe's fine-tuning, but it does so by invoking an unimaginable, unobservable infinity. Critics argue this is a philosophical surrender, a way to explain our incredible luck by saying that every possible lottery ticket was printed, so of course a winner had to appear. It answers the question of why our universe is so bio-friendly, but at the cost of moving the ultimate explanation permanently beyond the reach of any conceivable experiment. The most intimate and mind-bending layer is the Level 3 multiverse, born directly from the mathematics of quantum mechanics. This is the many worlds interpretation, where every single quantum event causes the entire universe to branch. Every time an electron changes its orbit, every time a radioactive atom decays or does not decay, reality splits. In one branch, you turned left on your way to work, while in another, you turned right, and both versions of you are equally real, living out the consequences in separate, parallel streams of existence. This model is mathematically elegant and solves the bizarre problem of why quantum objects seem to exist in multiple states until measured, but its implications are staggering. It suggests an almost incomprehensible proliferation of realities, with new universes budding from every moment and every decision. The controversy here is not just about testability, but about the sheer ontological extravagance. Are we to believe that an infinite number of near-identical worlds are constantly being created, each one as real as our own, yet forever beyond our perception? Proponents say the math demands it, while opponents see it as a failure of imagination, an unwillingness to find a deeper, single-world theory. Each level of the multiverse pushes the boundaries of science further, forcing us to ask if the ultimate nature of reality is something we can ever truly know, or if we are forever confined to just one small corner of an infinite and ultimately unknowable whole. The eerie silence of the cosmos might be the most compelling evidence for the simulation hypothesis. We gaze out at a galaxy filled with hundreds of billions of stars, many hosting planets that could cradle life, and we are met with a profound and unsettling quiet. This is the Fermi paradox, the bewildering contradiction between the high probability of alien civilizations and the complete lack of any observable sign of them. If our universe is a simulated construct, this great silence suddenly makes a perverse kind of sense. The beings running the simulation, whoever or whatever they are, may have chosen to only simulate one instance of intelligent life to conserve computational resources. Why render the intricate details of 1,000 different alien societies when a single, isolated humanity serves the purpose of the experiment, whatever that may be? Alternatively, other civilizations could be simulated, but the programmers have simply placed them beyond our observable horizon, quarantining us in our own cosmic sector to see how we develop alone. This idea blends astrophysics with science fiction and philosophy, creating a controversial but fascinating potential solution. Yet critics are quick to dismantle this logic. They argue it is a classic argument from ignorance, a fallacy that uses a lack of evidence as evidence for a specific claim. We do not know why we have not found aliens, so we invent an untestable reason that conveniently fits our pet theory. This does not actually solve the paradox with any tangible evidence. It merely explains one mystery by invoking another, even deeper mystery. The simulation hypothesis offers a seductive answer to the question of where everybody is, but it ultimately leaves us staring at the same silent stars, now wondering if their emptiness is a design feature of a reality we can never truly prove is our own. This cosmic fine-tuning is often presented as the most powerful evidence for a divine architect. Proponents of creationism and intelligent design point to the universe's physical constants, values that seem set with impossible precision. If the gravitational constant were even slightly weaker, matter would never have clumped into galaxies and stars. If it were marginally stronger, the universe would have collapsed back on itself in a fiery crunch shortly after the Big Bang. The strong nuclear force which binds atomic nuclei together is balanced on a razor's edge. A few percent weaker, and only hydrogen would exist with no complex atoms for planets or life. A fraction stronger, and all the hydrogen would have fused into heavier elements in the early universe, leaving no water or the building blocks of biology. This apparent perfection, they argue, cannot be a cosmic accident. It points toward deliberate design, a universe crafted specifically for life by an intelligent cause. The scientific community, however, offers several powerful counter-arguments that reframe this apparent fine-tuning. The first is the anthropic principle, a simple but profound logical observation. It states that we can only observe a universe capable of producing observers. If the constants were any different, we would not be here to notice. A lottery winner might marvel at their incredible luck, but they never consider the millions of losing tickets. Our presence necessarily selects for the one winning cosmic ticket that allows for our existence. Another compelling counter is the multiverse. If our universe is just one bubble in an infinite froth of realities, each with randomly different physical laws, then it is no surprise we find ourselves in the one rare bubble where the numbers are just right. There is no need for a designer, only the sheer statistical inevitability that in a landscape of infinite possibilities, a bio-friendly universe had to appear somewhere. A third possibility is that these constants are not independent, free-floating knobs waiting to be set by a divine hand. A future, complete theory of everything, perhaps a unified theory of quantum gravity, might reveal that these values are mathematically necessary and locked together. They could be the only possible outcome, the inevitable result of a single, elegant equation from which all of physics flows. In this view, the universe is not fine-tuned, but simply tuned, a unique and unavoidable expression of the fundamental laws of existence. The controversy, then, is not about the precise numbers themselves, but about what we infer from them. Is this perfection the signature of a creator, or merely the necessary condition for our own curious gaze into the cosmos? And so we return to the place where our cosmic journey began, to the very first moment of the Big Bang itself. This is the singularity, the ultimate point of controversy. According to Einstein's theory of general relativity, if you rewind the expansion of the universe all the way back, you reach a state of infinite density and temperature, a point where all the matter and energy in the cosmos was crushed into an immeasurably small speck. At this singularity, the very laws of physics as we know them cease to function. Gravity, time, space, and causality all break down into mathematical nonsense. For decades, this was accepted as the stark, inexplicable beginning of everything. But many physicists now see this infinite point not as a physical reality, but as a glaring sign that our theory is incomplete. It is a mathematical cry for help, a signal that general relativity, for all its power, cannot handle the extreme quantum fury of that first instant. The debate now rages over what truly replaced that singularity. The leading contender is a theory of quantum gravity, which seeks to unite the large-scale rules of Einstein with the tiny, probabilistic world of quantum mechanics. In this new picture, the singularity is not a sharp, definitive point, but something blurred and smeared. The violent beginning is replaced by a transition, a quantum bounce or a fuzzy state where the concepts of before and after lose all meaning. Imagine trying to pinpoint the exact moment a cloud forms in the sky. There is no single, sharp boundary, just a gradual condensation from a diffuse mist. In a similar way, a quantum universe might not have a clear-cut beginning. It could have emerged from a previous state, or it could simply always have been, with the Big Bang representing a dramatic phase change rather than an absolute start from nothing. This means the universe may not have had a true beginning in the classical sense we intuitively understand. There may be no first moment of time, no ultimate click of the cosmic clock. The search for what came before the Big Bang might be as meaningless as asking what is north of the North Pole. The singularity, that symbol of ultimate origin, might dissolve into a deeper, more mysterious, and perhaps beginningless quantum reality. 25 different paths wind back to the same profound mystery. We have journeyed from the explosive singularity of the Big Bang to the silent, eternal cosmos of the steady state. We have explored the possibility of living in a hologram, a simulation, or one bubble in an infinite cosmic foam. We have considered the universe as a quantum fluctuation, a black hole interior, and even as a mathematical structure itself. From the rhythmic cycles of death and rebirth to the stark possibility of a divine designer, these theories represent the farthest reaches of human curiosity. Some are backed by complex mathematics, while others stand as philosophical challenges, but each one dares to ask the ultimate question. This vibrant debate, this healthy and necessary controversy, is the very engine of scientific discovery. It is the process of proposing, challenging, and refining ideas that pushes our understanding forward, forcing us to look deeper and think harder about the nature of reality. None of these theories may be the final answer, but the search itself is what matters. Perhaps the greatest mystery is not how the universe began, but that we are here, able to ask the question at all. So, which of these 25 ideas resonates most with you? Was it the cosmic hologram, the endless multiverse, or the timeless cycles of eons? Let us know your favorite theory in the comments below, and subscribe to continue exploring the deepest mysteries of the cosmos.